All right, it's all happening now. This is going to be row space time. It came from row space. All right, so we've had column space, null space, now we have row space. Seems perfectly fine, right? We've had column space, which is take all the linear combinations of the columns. What does that give us? That's some subspace of Rm. We could do the same with the rows, right? Just take all linear combinations of the rows. Why not? And that may or may not be a meaningful thing, but in fact, it turns out to be totally awesome and a big deal, right? So I'm gonna have a, right, so it's a thing. That's what I just said. We're gonna see what it means for Ax equals B. And there'll be many, many little big deal pieces, lots of things we already know, done a lot of work, so this is all just sort of fitting things together. And then I'll talk a little bit about the big picture. This will be for Inigo, which is the 2x3, and Fezzik, the 3x4, the one that does not exercise or need to. Okay, so story, right? So the story. So the idea, whoops, is that, let's make more things. So the story is this. We'll just call it row space to start with. We'll have a really, you'll see it's quite spectacular. We have a CA, right, for column space and NA for null space. Okay, I'm very excited for you. So notational joy is coming. So row space, right? So row space of A is equal to, it's just, this is by definition, right? It equals all linear combinations. Such an exciting term, linear combination. Phrase, combinations of the rows of A. All right, so it's a subspace. Where do the rows live? Subspace of N. So that's where null space is, right? So this is an M by N. So where null space, interesting, lives. So something to do with null space. All right. So it's a fine space. So contrast with column space of A. I'm going to come back to it, but let's column space of A, which is a subspace of Rm. You might imagine the transpose is going to matter here, right? Because the transpose of A, then we'd flip column. If we take, so A transposes row space will be A's column space, and A transposes column space will be A's row space. I think I said that right. But they're a little, right, they're connected. Very nice, very nice. It's going to happen. Okay, so lots of big deals. What, so let's kind of start off with how it helps us. That's short for, yeah. So big deal number one. Big deal. The cat is still asleep. Doing a good job. Hard work being a cat. Pratchett. All right, okay. The monks, they never sleep. They're always just sitting there. Kind of just watch me. Okay, so big deal number one is this. So if X is in, we're just, as I said, we're just going to A's row space. Right. Maybe this is a bit hard to see straight away. Then, right, so it's some combination of these vectors, then these rows, then A times X, it's just sort of an observation, is not equal to 0 unless X equals 0. This is just kind of, we're connecting a little bit to the null space thing, right? So X is not in the null space of A unless it's 0. So let's look at Inigo. Right, we have A equals 1, 2, 2, 4, 1, 2. row space. Row space for this thing, it's all linear combinations of these two rows. So it's kind of, you know, we have to figure out how we're going to do this. But so clearly, dangerous word, clearly the row space of A, because the second row is a multiple of the first row, other way around, of A is actually just equal to all X in R3 such that X is some constant times 1, 2, 1. C is an element of the real numbers. Good. All right. So they're the only, that's the only, right? So we can take, this is just sort of an example, right? So this is not proving anything, but let's just do it. So 1, 2, 2, 4, 1, 2 times C, 1, 2, 1, right? So this is any, so this character, this is the matrix, this is representative of any vector in row space of A. So multiply those things together. There's a C, which is just a constant, 1, 2, 1. So it's a dot product of 1, 2, 1 with itself. Interesting, right? So inner product of a vector with itself gives the length squared. Pythagoras, right? So 6. And then we have double that, right? So there'll be 12. And we can pull that 6 out. So it'll be 6C, 1, 2. And this is, which is clearly in the column space of A. That has to be true, right? A times X has to be in the column space of A. So this is a, has to be true. Right, the columns of an ego are simple, right? They're multiples of each other. So this is just something times 1, 2. Okay. Okay, so to get to A times X only has some substance, it's not 0, if X is in fact expressible as a linear combination of the rows, right? And null space vectors are at right angles to the rows. So these are things that live in the row space. So what is going on? So recall, so let's go back to this. So recall what we were trying to do with AX equals B. Right, this problem, AX equals B. We got to this observation that we had X equals X particular plus X homogeneous. And I said, we'll find that that's a row, it's an R for row, and this is Xn for null space. So let me annotate those things a little bit. So this is particular, homogeneous, solves the null space equation. We're trying to bring all these things together. This is row, and this is null. Okay. Okay. Okay, so the idea is this then, that our problem A times X, let's just call it particular for a second, H, like this, that's an H, equals A times XP. This is the part that's equal to B. Let me add this, and this is A times XH. This is the part that's B, right? That's the thing that actually gives us the solution, and this is 0, right? Could be many possibilities. Maybe infinitely many. And that is the same as, this is the case that the null space of A is not equal to just 0. Hope that's okay to stick that in there. Okay, so the story now is that if we want to make something that's non-zero, XP must live in the row space of A. All right, let's keep going. Let's keep going. Lots of pieces, and we'll have many, many examples to come, or really getting into it in depth. So, okay, right. So this is a big deal. How do I do it? Number 2. This is a huge thing. So any x in the row space has to be orthogonal at right angles to any x. Got carried away. Any x in the row space of A, really big deal, is perpendicular, orthogonal, that's a comma, orthogonal. Let me do it like this, at, boom, these things, delete whichever one, at right angles to any x in the null space of A. Right, so I sort of said this before, so right, so 1, 2, 1, 2, this is our example, right? This is A. 4, 2, this is A. And from before we had that the null space of A is, we did it in a particular way. We had 2 minus 1, 0 like this. It's a sad looking thing. Plus C2 and I think, yes, minus 1, 0, 1. This is from before. This is a null space of A from before. Right, and by this is A times a null space vector. This has to equal 0. So the inner products of the rows and these vectors in null space are 0. That means they're orthogonal. Good, good. So so we're talking about things that can be really distinguished clearly, right? Even better. It's going to be even better. Big deal number 3. This is great. Okay, wow, so many things. Big deal is the row space of A. This is the free thing. Is the same as the row space of R, the reduced row echelon form. This is terrific. So you've done all the work. So everything you've done so far, we've been producing reduced row echelon forms for A. That's it. You've got it. You've just it's sitting there, and this means what you've got is a basis, right? Which means a basis, a beautiful basis for the row space of A is equal to the non-zero rows of the reduced row echelon form of A. So our examples, so in Nego we had 1, 2, 1, 0, 0, 0. Right, that's the reduced row echelon form. So I'm just, A is obviously changing for each one. So our basis is, that's it, 1, 2, 1. And we know because we've made these pivot columns, they only have a 1, right? In one place, they look like the identity. We know it's a basis, right? And the better example for us right now is A, this is Fezzik. Fezzik ended up as 1, 2, so I feel I should write these so you know what they are. This is Inigo. This is Fezzik. There's no defense for this madness. We will do it. 0, minus 1, 0, 1, 2, 0, 0, 0, 0. So basis, the basis here, is, just read them off, right? Goodness, yes, so much goodness. 1, 2, 0, minus 1. Just sitting there, we didn't have to do any more work. 0, 0, 1, 2. So if you go back to Fezzik, and this is the same as saying, as we did early on, that A equals LU, right? That we could reconstruct L out of A out of U's pieces, and L is a combining matrix. The reduced row echelon form is the same thing. Now we've gone further, right? So we can always reconstruct A if we remember all our elimination matrices. Here's the piece that's really important, right? They're clearly independent. So the rows are independent, linearly independent, right? There's no way we can make these rows out of each other because of identity sitting in the pivot columns. Wow. Wow. The monks have not, yeah. I mean, there are some of those evil monks, you know, and there's like demons and stuff associated, but that's not what's going on here, right? These are totally good guys. The monks of the rectangular numbers in boxes business. Okay. At least so far. All right, that also tells us the dimension. Oh my gosh, right? Because we know how many rows there are. There are rows that are non-zero. So we know the dimension of row space. And it is the same as dimension of column space. Big deal number 4. Wow, so many of these things. Big deal number 4. The dimension of the row space of A, you could write it like this, equals the dimension of the row space of the reduced row echelon form of A, because of the same, because same, to use sort of a modern construction, because same z's, hyphen z's. Let's do it. I mean, if we're going to write such a quality word. And that's R. That's the number of non-zero, right? Non-zero rows equals the number of non-zero rows. By definition. Suspicious, very suspicious. It should be very suspicious. This is where we're getting at how any matrix maps some subspace in Rn to some subspace in Rm, and those subspaces are the same dimension, because matrices, they can crunch things, right? They can send things to zero and so on, but the parts that they like, you know, if it's a plane here, that's the row space, it gets mapped to a column space and it'll be just stretched, rotate a little bit, nothing weird and nonlinear. It doesn't matter what the big dimensions are around them. There's a plane, goes to a plane. Okay, a little too much. So the dimension of A's row spaces are huge, huge. Amazing. Right, same as the dimension of the column space of A. Wow, so great, so great, so great. This is something we'll get to in the next few pieces, but we'll just notice it, that this is big deal number 5, the dimensions of the row space of A, which is, and row space of A and the null space of A, those two dimensions add up to, so think about that quickly, add up to M. Wrong, N, which equals, just in order, maybe I should do it like this, R plus N minus R. So there's a sense here that these two subspaces neatly, because they're at right angles, they neatly divide up their ambient space. So we're going to get that. Let me just say it here, I suppose. So for example, this is for Inigo actually. So this is row space. Let's say this is basis 1, 2, 1. And then there's a 0 vector here. And then in here we have two vectors. This is not necessarily in the right direction or anything. Maybe I should make them, right? There's a basis vector here, there's a basis vector here, and a basis vector here. And as we've sorted them out, right, so these are just how they naturally came out. Let's say, and this is, so this is row space, and this is the null space of A, plane in 3D, in R3 I should say, R3. This is a line in R3. So the dimensions are adding up. Okay, that's good. And what else? So we know that the basis for this one, because this is a nego. Yeah, minus 2, 1, 0, and minus 1, 0, 1. So we have two vectors. Look at them independently, right? So these are at right angles, right? So this one, dot product with this one, inner product, minus 2, plus 0, right? That has to be true. So we see the basis vectors are orthogonal to each other. Not these two, right? Not these two, but the ones from the different spaces. Dimensions add up, right? So in this case, the dimension of the row space of A is 1, is R equals 1. The dimension of the null space is N minus R, which is, so they have to add up, 3 minus 1, which equals 2, right? So 1 plus 2 equals 3. Advanced math right there, 1 plus 2 equals 3. All right, so there should be some loud organ music, lightning. So maybe the budgets are a bit of an issue, copyright too. They keep getting, yeah. So let's just now imagine, it's an important detail, loud organ music and lightning. It is a bit rainy today, but I don't think we're quite in the lightning category. Okay, good. Polish. Okay, that's pretty cool. That's pretty cool. So these, so I'm going to say it with one more piece. So the row space and null space and the null space of A neatly divide up Rn, right? So they break it down. The subspaces, their dimensions add up. They're at right angles to each other, which, yep, very good, very good. Okay, so that's pretty awesome. Wow, cat is just gone. Okay, so I've been writing row space, row space, row space. And we're lazy, like the cat, so we want to have a better notation, and we want to see deeper things. So here's a great thing. So an ego, so this is big deal, number 6, I think. Oh my gosh, really? So excess. Big deal number 6 is, consider a transpose for an ego. So we do that, right? So now we've got this. A transpose is, we'll just swap 1, 2, 1, 2, 4, 2. An ego is back here. Right? Just take the transpose, flip. Well, now this is the thing where the column space is the row space and the row space becomes the column space. So we now see the row space of A, right? So the rows are here, they're now columns. Row space of A is also the, fill in the blank, also the something space of something. Albatross. The A actually stands for albatross. No, it doesn't. A transpose. Wow, I could draw albatrosses. Of the column space. It's the column space of A transpose. Wow, okay. fantastic, right? So that means actually, so there's another piece. So in fact, okay, let's see, too much. So the notation will be the column space of A transpose. It will feel a little odd, I suppose, but it connects things properly, right? So it means that we don't end up with some other extra notation. It helps us tie things together. So if we understand this, then we really understand things. So equals the row space of A. So we just need, so there's nothing new here, right? We've had these before. Yeah? Yeah, we're repurposing. Or just seeing a deeper, because of a deep connection. Plus we've already used R, so we get, anyway, this is the big deal, right? This is huge. Okay, there was one last pretty amazing thing that it just opens things up completely. Big deal number 7. Because we've got this connection, and we've seen just how nicely, yeah, here it is, just how awesomely, right, the basis for row space. So we kind of had to fight for a basis for column space. We did. We only really got it in that just recently when we noted that the pivot columns of R are the only ones that matter in terms, we can produce the free columns in R, the reduced row echelon form of A. And then we know that the columns don't get changed, the relationships don't get changed, right? That's what I should say. The relationships between the columns do not get changed by row reduction. So the pivot columns of A form a basis for column space of A. Now that's a little bit of work. It's not great. Here it's much simpler, right? The basis for row space is just sitting there in the reduced row echelon form of A. So we can get a right, this is what we'll do. So we find a third way, a third and final and totally bestest way, let's get the right English in there, the bestest way for finding the column space of A. Right. Right. What else do I have in here? Yeah. So the column space of A transpose, this is an important thing. So if we take the reduced row echelon form, find the reduced row echelon form of A transpose. So take the transpose of A, right, and then read off. So essentially we take the columns of A, we flip them and make them into rows, now do a row reduction, and that will give us a nice basis just sitting there, but it's not, it is for the column space of A because we turn columns into rows. And then read off basis vectors for the column space of A. And I feel like I should put some examples up. Yep. This is awesome. Okay. So this gives us a reason now for finding the reduced row echelon form of A transpose. There's a deep meaning. So this is, I just want to make a very important note. So note, you cannot, this is not true. Don't do this. The reduced row echelon form of A transpose is not equal to, in general, if it's right, not in general, the reduced row echelon form of A transpose. That's an in general. Well, if you're doing, this is bad understanding. This is a, right? Horrible. It's gone horribly wrong. Okay, so just don't do that. So, this is really huge, right? Fantastic. And we don't have to have b's anymore. We don't have to find an arbitrary b. We can just work with reduced row echelon forms, which are really nice. Right, the b's get jumbled up. It's a messy thing. This is much better, much deeper. I have to think about it a little while, but it's totally awesome. So let's do a couple of examples here for this last big deal. So examples are A equals 1, 2, 2, 4, 1, 2. Take the transpose. This is an ego. 1, 2, 2, 4, 1, 2. And do reduced row echelon form on this, right? So A transpose. I'll just do it simply for this one. You should be able to see how to do it. Row 2 prime, right? We're trying to get rid of this and this is equal to row 2 minus something times row 1. We always do the same thing. We can do row 3 at the same time. That's weird. Row 3 minus something times row 1. And it's 2 over 1 and 1 over 1, right? It's a simple thing, I know, but we're just doing things for form. So we end up with, of course, 1, 2, 0, 0, 0, 0. So this vector here, 1, 2, is a basis for CA. So it matches up with what we had before. It won't necessarily be the same, but it is exactly the same as what we had before. An ego. Physic. All right, and then we'll finish this section. I think that's enough, yeah. So we have A transpose. Quite hard to turn over this. Imagine wrestling with Physic. 4, 4, 12. So we take, if you want, you can call this character Andre the Giant. So 4, 10, 18. And you do all this reduced, right? So we do all this stuff. I can leave that for you to work out. But you can see 2 times the first row from the second one, blah, blah. Okay. And we'd end up with, so this is the pain and suffering, row reductions, row ups, plus tears, frustration, yep. Calling home, saying why did you make me do this? So you do all these things, and they have 1, 0, 2. Your parents should just say, because we love you. Okay, there it is. This is the story for this one. It's good. Rank is 2. We expected that. So that would give us, in this case, 1, 0, 2. We're reading them off, and 0, 1, 1 is a basis for the column space of A. And you can think, so this is it's not as obvious as perhaps it's not as clear as the first one, but it has some very nice properties, right? So the identity matrix is here. Really nice stuff. Really nice stuff. The identity matrix is here too. It's just, there's only one. It's a 1-by-1 identity matrix. Super nice. Super. This is the best, right? So the identity matrix now always appears. It's a really nice looking basis. It's really clear why it is a basis. It's got an identity matrix sitting, so you can't make one out of the other, or if there are many of them. Huge. Okay, so the REFSs really mattered, and I think we are good. I think we are pretty good. Yeah. So let's recap. Big deals. Row space. We just said, all right, let's think about row space, and then start to look at what it means. We have a few things. So the first is that for AX to produce something that's non-zero, then the x actually has to be some linear combination of the rows. If it's, this is the only way you're going to get something, if that kind of makes sense. If it's at right angles to the rows, then it's actually in null space. So we need something that has some component in row space. And if it's, right, okay, right. I mean, the way I was saying, I guess, is that, yeah, if x is part of row space, then we're going to get something non-zero. So that's good stuff. We had that, then we had that the x in row space is normal to, or at right angles to any x in null space. Then we have this beautiful thing, the row space. While we do a lot of damage to the columns, we preserve the relationships between the columns when we do row operations, but we don't, and we mess with the rows, but we don't change the space, the subspace that all linear combinations of the rows of A and all linear combinations of the reduced row echelon form of A, they both produce the same thing. It's good. We have the dimension is R then for row space. It's the number of non-zero rows, which is equal to the number of pivots, which is our definition of rank. Totally amazing. And then we have that the dimensions of row space and null space add together. And just as an example here, we're going to see it more deeply. They add together, and because they're also at right angles, it looks like they're going to neatly divide them up. And the word, so later on so soon we'll talk about these as being orthogonal complements. And that doesn't mean nice things you say to people. That could be interpreted in different ways. But these subspaces are orthogonal complements. They neatly divide up the space. All right, and then A transpose just comes riding in and is unbelievable. And we see that actually row space is the column space of A transpose. And then even better than that, well, no, that's, I mean, another thing that comes from that, which is also awesome, is that the reduced row echelon form of A transpose gives you, that has sitting in its rows a basis for column space, right? Right. The row space of A transpose is the column space of A. Let me say this. Right. So the row space of A transpose equals the column space of A. Maybe I didn't write that down. All right. So lots of pieces here, and this is great. So when we solve our problems, yeah, the one that's going to get to B, if B is non-zero, is a vector in row space. So the big picture is coming. Big picture is coming. I'm not going to draw it here, but the big picture is coming for all of these examples. We're going to have row space and null space on this side, and then there's column space over here, and then something else, and that is next.